Hi, in this video, we will show how to use our product, the AI and Analytics Engine, to build a machine learning solution tailored to any specific need without needing to code. We'll take up a specific use case from the banking industry to illustrate the process, predicting the status of loans 5 years after they are granted. Will they be on track to be repaid in full, or will they be in arrears? To proceed with this use case, we will need to use the Build from Scratch option on our product. This option allows us to define a series of steps and configurations that make up the machine learning solution that we plan to build. It thus gives us an unconstrained and flexible option that can be tailored to any use case in any industry. It does not require us to code and hence allows us, as a data analyst or data scientist looking to enhance our productivity, to focus our efforts on the more interesting aspects of our job, such as applying domain knowledge and using problem-solving skills. Now let us dive into the datasets that we have been provided with in this use case. The loans dataset contains information about the loan applications, such as the loan ID, the applicant's checking account ID, the date the loan was granted, the loan amount, the loan duration, the repayment amount, and the loan status. The loan status is a categorical column with 4 categories. A, which means finished with no problem, B, which means finished with debt, C, which means running with no problem, and D, which means running with debt. This column will be transformed into a binary column with 2 values that we want to predict: no problem and debt. The client's dataset contains customer records with the following attributes: gender, date of birth, and the location ID. Finally, we have a dataset of historical records of transactions in the customer's checking account. Each record contains the account ID of the customer, the transaction date, the transaction amount, and the type of transaction, and other attributes such as the balance, etc. Now let us dive straight into the engine to start building our loan status prediction application. The first step is to log into the engine. After ensuring that we are in the right project, let us choose the Build from Scratch option. Next, we are prompted to choose from 2 options. Here, we need to choose regression or classification, as the task that we have for our banking use case is classification. We are now taken to the App Builder view. It contains the steps to prepare data, define what to predict, select features, and build models. Next, let us add and prepare the datasets that we have been given. We can either add existing datasets in the same project that we have previously imported, or import them new. Since we do not have any existing datasets, let us proceed with the import option. Under the import methods that show up next, we choose the file upload option and then choose the file that we want to upload to proceed. Let us first upload the client's dataset. The schema that the engine has detected looks satisfactory, especially since it has correctly detected the type of the date of birth column as date time and all other columns except gender as numeric. Upon confirming the creation of the dataset, we are taken to the App Builder where we can see the added dataset. We can examine the column statistics and visualizations with the View Analysis icon, or remove the dataset from the application but keep it within the project with the cross icon. Let us proceed to add the other 2 datasets, loans.csv and transactions.csv. When we import these 2 datasets, we are going to keep the date column as a text column and not let it be inferred as numeric. We will later use the engine's data preparation tools to convert the column into date-time type with an appropriate format. Once all the datasets are added, we can see them back in the App Builder's Prepare Data stage. The next step is to prepare these datasets. The first one to prepare will be the transactions dataset. To prepare a dataset, we first click on it and then choose the option to prepare data. As you can see, we have three options. Let us choose create a new recipe and name the recipe prepare transactions data. We are then taken to the recipe editor. We can start adding actions right away to prepare data. On the recipe editor, we can see a preview of the dataset after the added actions have been applied. We haven't added any actions yet, so we are just seeing the preview of the original data here. To add actions, we use the right side panel. The next step is to prepare datasets. The first one to prepare will be the transactions dataset. To prepare a dataset, we first click on it and then choose the option to prepare data. As you can see, we have three options. Let us choose create a new recipe and name the recipe prepare transactions data. We are then taken to the recipe editor. We can start adding actions right away to prepare data. On the recipe editor, we can see a preview of the dataset after the added actions have been applied. We haven't added any actions yet, so we are just seeing the preview of the original data here. To add actions, we use the right side panel. We first want to ensure that the dates are parsed correctly and not stored as a text column type, as you can see currently. To find the action that can achieve this for us, let us type date time in the search bar of the action catalog. The convert text to datetime action looks appropriate, hence let us go with it. We add the desired action and configure it properly. Here we need to specify the input column as date. We then specify the datetime format as percentage small y, percentage small m, percentage small d, meaning 2-digit year, 2-digit month, and 2-digit date with no spaces or characters in between. We then add the action. We can see on the right panel with the summary of what it's doing. On the table preview to the left, we see that the type of the column has changed to datetime and the values are parsed appropriately. The next action that we want to apply is to translate the type column to have English language labels. Let us use a mapping for this. Having ensured that we have added the actions we want in the recipe, let us finish it by clicking the Run Recipe and provide a name for the output dataset. Once we confirm the name of the output dataset, we can see that the recipe and the output dataset are being generated in the prepared data stage of the app builder. We do not need to wait here. We can proceed to the next dataset, which is loans. Next, let us prepare the loans dataset. We follow the same process to create an appropriate recipe. Here is a summary of the steps. We have converted the date column to a datetime type column with an appropriate format. We have renamed the date column to loan date and the amount column to loan amount. And we have also applied the mapping to convert the 4 categories of status into the 2 categories that we want to predict. We finished the recipe by issuing Run Recipe again. After some time, we can see both recipes have finished running and have produced the prepared datasets as outputs. This ends our initial cleaning and preparation process. To proceed further, we need to create a single training dataset from the 3 datasets that we have imported and prepared. Let us take a look at the view guide pop-up for further guidance. First, we need to prepare a dataset of training examples. Each training example should be a list of input variables to the model and the value that the model is expected to predict. To build such a training dataset from our prepared data sources, we first need a plan. What are we predicting here? As we know, each training example corresponds to a loan application, the target variable being, did the loan repayment face any problems? Which is what we have in the loan status column from the loans dataset. Okay, now that we have decided what prediction is needed, we need to think about the potential inputs to our model called the features. We need to create features from the data sources that we have been provided with, and we need to decide how we're going to create them. The easy part is to use the characteristics from the loans dataset directly. The year and the month the loan was granted, the loan amount, the duration, the number of payments set by the bank initially, etc. We can also match the loan ID with the client and obtain information about the clients from the client's dataset. Their gender, their age at the time of loan application from the date of birth column, and their location ID. Finally, we can use the client's transaction history leading up to the loan application date and compute aggregate statistics such as the minimum balance, average of different types of transactions, and so on. We finally have to join these results to get our final machine learning ready dataset. Let us first generate the aggregate transaction stats features from the transactions dataset. Before computing the aggregation, we need to join the transactions dataset with the loans dataset and filter out the transactions that happen later than the loan date to avoid temporal leakage problem, or in other words, data leakage from the future into the present that can lead to misleadingly high model performance. We can do the join by selecting the prepared transactions dataset and then selecting the merge with another dataset option this time. This process also creates a recipe but conveniently adds the action to merge 2 datasets on our behalf. We are shown different ways to merge with a dataset. Joins such as left join, outer join, inner join, etc. Looking up values from another dataset by key, looking up aggregate columns from another dataset by a key, and performing union of 2 datasets, in other words, row appending. Let us go with the join option as that is relevant to us. Click next. And we need to select the dataset to join with, which is the prepared loans dataset. Next, we choose create recipe. We are then taken to the recipe editor view with the join action open. Next, let us modify and confirm the join parameters as inferred by the engine here. Let us do a right join since we are only interested in transactions from the accounts that have a loan. Further, from the loans dataset, we keep all columns except for the account ID, as the transaction dataset already has an account ID. Save all the changes to add action, then we can see the columns added from the loan dataset as well. Next, we want to remove the entries where the transactions date is past the loan date, so that we do not leak data from the future into the past. To do so, we choose the filter action from the actions catalog. We then enter the formula date less than loan date to keep only the rows that satisfy this criterion. We now have the transaction history of each loan only up to the date of the loan application. From this, we can proceed to compute aggregate features from the transaction history of each loan applicant. Specifically, for each transaction type, we will be computing summary stats such as minimum, maximum, mean, median, and standard deviation for 2 key quantitative attributes, the transaction amount and the number of days elapsed since the last transaction of the same type. We will also compute the days elapsed since the last transaction of each type. To facilitate finding the average interval between transactions of each type, we first want to compute the lag function of the date column, partitioned by the account ID and type, ordered by the date column. This can be accomplished with the shift rows action. Let's name the output column produced by this action as previous date of same transaction type. After adding this action, we can compute the number of days elapsed between the date and the previous transaction of the same type using the compute time elapsed action. We name the output as days since last transaction of same type. Note that we need to specify the optional time unit parameter as days instead of leaving it to be the default setting of seconds. Now, to compute multiple stats for each transaction type, we can make use of the reshape data into pivot table action. We need to specify the group by column as the account ID, the pivot column as the type, and the pivot values as the different categories that appear in the type column, namely credit, withdrawal, and withdrawal cash. For each aggregation that we want to compute, we just specify the column to aggregate, the aggregation function, and the prefix of the output column. We can add multiple aggregations as I have done here. Upon saving the changes, we can see the pivot action is added and the aggregated features are generated for each pivot value: credit, withdrawal, and withdrawal cash. After this, we add a few more actions. The reasoning for these actions is as follows. After we added the pivot action to compute aggregates by transactions type, the columns from the loans dataset were lost. So we get them back by joining again with the prepared loans dataset using the same join keys. We then join with the client's data to get the demographic features of the client, such as the date of birth and the district ID. We then extract more features from datetime columns, such as the days since last transaction of each type at loan application day and the age of the person in days using the compute time elapsed action. We then divide by 365 to get the age in years. As a final step, we drop all columns of datetime type except the loan date column. We also drop the intermediate column storing the age of the customer in days instead of years. We retain the account ID column and the loan date column as we want to join again with the transactions dataset to get the minimum balance later. We can now run this recipe and produce the output dataset. We have now generated some aggregate features from the transactions dataset. We then join with the attributes of the loan and with the attributes of the clients. These aggregate features are separated by the 3 transaction types we saw earlier. We need one more important feature from the transactions dataset, which is the minimum balance at the time of the loan application. To get this feature, we start again from the prepared transactions dataset. We will be joining with the prepared loans dataset and the dataset output by the latest recipe that we worked on. Here is a summary of the recipe. We do a right join with the prepared loans dataset and filter out the transactions whose dates are earlier than the loan application date. We then compute the minimum balance feature by grouping by the account ID column and aggregating the balance column. We then join with the features that we generated before using the account ID column as the key. We name the output of this recipe as a final training dataset. Next, we configure our prediction task to start building models. If you're a novice user and do not want to wait, you can proceed to the end and just let the engine select the best configurations for you based on your acceptance criteria. If you're an advanced user and want to manually configure everything, that is also possible. You do not need to wait for any recommendations to be generated. In case some configuration is found to be incompatible with the analysis results on the full dataset, you will be notified with an error message, such as if you chose a numeric column for a classification target, or if you have too many classes in your target column for a multi-class classification, or if your train test split configuration is invalid for the dataset and is out of range. Next, we will explore how the app is built and how we can explore trained models. Once we have completed all configuration setup up to the build model step, we are taken to the app summary page. It shows the progress status of various processing steps. When the app finishes processing and models are trained, the top model's performance will appear on the right side along with the prediction quality. We can see 71.72% prediction quality, which is great given that the ratio of the dead to the no problem cases is very small in the dataset. Upon clicking the model name from this section, we can see the details of the model. It shows further details about the model and what you can do with it. We can click on the View Details card under Performance and see a detailed evaluation report, including various metrics and evaluation charts. In the Feature Importance tab, we can generate feature importances so that we understand which features impact the model most. This will also generate the prediction explanation for a sample of predictions generated on the test portion available in the next tab. Having made sure we are satisfied with the model's performance and with the insights that explain how the model works, we next want to make predictions with the model with new data. We first select the Make Predictions button from the App Summary page, and then choose to make either a one-off prediction or to run periodic predictions on a schedule. Either option will take us to the prediction setup page, where we can see the recommended model selected for us already, but we have the option to use a different model if we want to. In the next step, we have the prediction pipeline builder. First, we have the placeholders to add the input datasets. We also have the links to the corresponding datasets used at the time of training under each placeholder for guidance. Here we can either add a dataset directly, or we can connect to a data source such as a database connection to ingest data from a table on a periodic basis. This would be useful if we were using the schedule periodic predictions option. Once an input dataset is added, the corresponding recipes will be populated as its child nodes, following the same data preparation steps that were applied to the dataset at the time of training. We can also remove these recipes and add modifiable copies of the original recipe if we want to make changes to the training recipe. This is quite common. It might be necessary, for example, to remove recipe actions added at the time of building the app to generate or modify the target column. After adding all the input datasets and the recipes, and all recipes and model inputs are validated, the configuration would be considered complete. And we can proceed to the next step. The prediction will appear as a tabular dataset with these additional columns, along with the features used to make the predictions, which is the output of the final recipe before the model. In the next step, we can configure the names of these prediction output columns. Here, since the use case is binary classification, we can also choose a threshold to be applied to the probability to get the binary label. After this, we can optionally define output destinations for the predictions. The same prediction can be sent to different output destinations simultaneously. This can be either to a project within the organization, with the current project being the default, or a database table connection. This step is optional. Predictions will still be available under the app for download or export later, even if no output destinations are defined at this point. If using scheduled predictions, the next step will be to configure how often the prediction should be run and when the prediction should be run. Once all the steps are completed, either a prediction run is immediately started if making a one-off prediction, or a prediction run will start at the scheduled date or time on a periodic basis. Once predictions are ready, we can preview them, download them as a file in CSV or other formats, or export them to the same or another project or to a database table. This completes our walkthrough video of using the build from scratch option. We have taken a specific use case to show that we can use the build from scratch option to build and use a custom machine learning application tailored to any specific use case. We prepared a machine learning ready dataset from multiple source datasets using the recipe function, and then defined the configurations for training the models, including selecting the target column, the features, and the algorithms. We then reuse the data preparation steps to generate a prediction pipeline and finally obtain the predictions from our model.